In principle, we can find the net magnetic field due to any distribution of currents by first writing the differential magnetic field dB due to a current length element and then summing the contributions from all the elements. For a complicated distribution of current, the required integration is a difficult task. However, if the distribution has some symmetry, we might be able to apply Ampere's law to find the magnetic field with considerably less effort. Ampere's law states that the dot product of the magnetic field B and the displacement vector elements dl integrated around a closed loop is proportional to the net current enclosed by the integration loop. The circle on the integral sign means that the integration path must be a closed loop called an Amperian loop. Let's take a look at the interpretation of this equation. As a general situation, we assume three long straight wires with currents 1, 2, and 3 placed perpendicular to the page. Currents 1 and 3 point out of the page and current 2 points into the page. An arbitrary Amperian loop lying on the plane of the page encircles currents 1 and 2, and we arbitrarily choose the counterclockwise direction of integration. To perform the integration that calculates the net field at one point P along the loop, we divide the loop into differential vector elements dl tangent to the loop. Because each wire produces magnetic vectors that lie on the plane of the page, the net field vectors will lie on the plane of the page too. The dot product B dot dl is equal to B cosine of theta times dl, where theta is the angle between the field vector and the length element. This dot product can be interpreted as the product of the length dl and the component of the field tangent to the loop. The integration is the summation of all such products. To determine the sign of each current, curl the fingers of your right hand around the wire in the chosen direction of the Amperian loop. If a current passes through the loop in the same direction as your extended thumb, that current is positive. Otherwise, assign a negative sign. As a practical example of the application of Ampere's law, we will find the magnetic field inside and outside of a straight wire of radius r that carries a current distributed uniformly over its cross-section. We assume the current is directed perpendicularly out of the page. Due to the line symmetry of the problem, outside of the wire, the field will draw circular lines centered on the axis of the wire. Encircling the wire with a concentric circular Amperian loop of radius r, the magnetic field has the same magnitude at every point on the loop. We shall integrate counterclockwise so that the length elements have the same direction as the expected direction of the field. Since the length element and the field have the same direction, the angle between those two vectors is 0 degrees, and the dot product inside the integral simplifies to B times dl. Since B has constant value along all points of the loop, we can take it out of the integral to get, but the integral of dl is just the summation of all the segment lengths around the circular loop that results in the circumference of the loop 2 pi r. The right-hand rule of the sign of the current gives a positive sign, and since the loop is enclosing the entire cross-section of the wire, the enclosed current is simply the current carried by the wire. Substituting equations 2 and 3 in equation 1, we get and solving for B, we get the magnitude of the field outside the wire. For the field inside the wire, we choose a circular Amperian loop inside the wire that encloses only a fraction of the current. With the current uniformly distributed, the current per unit of area or current density is and from that, we can obtain the current enclosed by a loop of radius r. The integral side of Ampere's law is the same as for part A, shown in equation 2. Substituting equations 4 and 2 in equation 1 we get, and after solving for the magnetic field, we get the solution. We can put the results for parts A and B together in a graphic form. For points inside the wire, the magnetic field increases linearly with R, which corresponds to a straight line in the field magnitude versus distance plot. Outside of the wire, the field drops as 1 over R, which corresponds to the field from a straight wire already known from the Biot-Savart law.